Hello, and thank you all for joining us. Today, we will be taking a closer look at simulation studies and how you can perform these in Solidworks. We will also be taking a look at some of the key limitations that we found throughout this process and how they can relate to other modeling softwares. I think it's first important to clarify what a simulation study is and what it's used for. A simulation study is a study conducted to simulate a set of conditions described by the user to determine the outcome of these conditions. So, three examples today that we examined are a bullet and a core-inch sheet metal impact, a bowling ball hitting a pin, and finally Thor's hammer hitting Captain America's shield. The first steps in any study are to create your parts. I won't be going through that today in the interest of time. You'll then line these up center to center, however you like the impact to be predefined. So once you've done that, you're going to come down to your bottom right. Okay. Oh, there we go. Create a new simulation study. You are going to go to nonlinear and dynamic, and I'm going to just name this example. Once you have done that, you will need to hit right click under connections and local interactions. This is what's saying which faces are connecting with which. So we'll go ahead and say the bullet is connecting with the flat plate. It's pretty self-explanatory there. Stick with me now. Okay. Now we need to define some more parts of our model. Make sure stuff doesn't move around. And I don't want to mess with that right now, just to be safe. That would really hurt. So, what you're going to do is you're going to come over here to Fixtures, Advanced Fixtures, use Reference Geometry, and I'm going to use the front part of this plate. And then I'm going to take for the secondary part, I'm going to use, the top plane of our plate. And then we will come down here to translations, millimeters, long here, and we'll leave it at 0. This will just help make sure nothing moves and it's stuck in place for the impact. It's important to note though, having as many definitions as you can will help speed up your model and not give it so many degrees of freedom. Okay, next, after that, you need to go into initial conditions, and we are going to select the bullet. We are going to select all of the faces, and we are going to then click as our secondary, and make sure this is on velocity, that is important. And you are going to click that plate. And then you can click which way you want to move along each plane here. And we are going to move this perpendicular to this back. Basically, the bullet is coming from the right, going to the left. Okay, and we are going to give this a speed of 500 meters per second. You may be asking yourself if that seems quite low for a bullet, and yes it is. And one of the many problems with Solidworks is that it cannot do over certain speeds, and if this bullet deforms enough and destroys the whole mesh, the simulation will fail. Important to note that. So, once we've done that, we're going to want to create our mesh. So, come down here, create mesh quality plot. What are our problems now? Let's just delete that. Let's make a new one. Create mesh quality plot. And there we go. Okay, we're gonna hit mesh, chart options, show min, show max. No, we don't care about that. This just puts wherever our chart will end up for us in SolidWorks. Settings, model, mesh, and you can pick your colors here. We'll just leave it how it's predefined. Alright, and that should be everything you need to do. From there you come up here and hit run this study. Okay, obviously this is just a warning telling you that if you switch off for any reason, you will have problems. So, obviously, you're going to have quite a few. Now, you can see our degrees of freedom, 56,000. That is not as high as we've had it before, but definitely makes it a bit of a challenge. It's going to solve every constraint that it has, and this will take upwards, I believe when we ran the study the first time, it was about 4 to 5 hours. So it's important that you know that when you go into this. So I'm just gonna hit cancel. I don't want to waste any of your guys' time. Yes, we're gonna terminate this. Any day now. Alright, now that brings us into some of the limitations that we had using Solidworks in this study at large. Anytime that you try and transfer over data, or you try and run it, or in this case of the bullet, since we initially tried 5,000 meters per second, the bullet obviously fell into 1,000 pieces, destroying this mesh. And so we would always get an error that said mesh broke, cannot analyze, and it would fail. And of course it would do this at the 3.5–4 hour mark. So while we do technically say that we have results, and it'll show it right now, we had to just keep reducing our values until we got to a point that our material wasn't going to fail. And that's how we got to this point. It's just checking and checking and checking over and over again. And with 4 hour iterations, it's really important that you can make some assumptions and limit the time. You don't need to have a huge mesh on your plate, that's flat. You can define it. You could add some damping. We didn't add damping. That was part of the reason that it took so long. So that's a big reason why we had a lot of issues getting stuff to run, and hopefully that'll help you when you do your mesh or your simulation. Next, we looked at the bowling ball hitting the bowling pin. First, we're going to look at the displacement graph. We did a similar process as I outlined beforehand. We can see that there's going to be high levels of displacement, but then when we look at the von Mises diagram, we see that the only place that there's stress is right at the contact point, which makes perfect sense with what we know the real world is going to have, and that is a key part of what computer simulations allow us to do, is take what the physics of our world, give it to the computer, and then have it run our models without us having to create them in real life. While it may take hours to run these programs, it'll save us countless hours in manufacturing and material costs if we can know the outcomes before we start building them, or at least get a very good measurement and a good idea of what can happen. Alright, now the moment you all have been waiting for is Captain America's shield and Thor's hammer, the big mamma jamba. So, key things to note here. For this application, we decided to basically act as if the shield was on the ground, so these straps do nothing, they're purely decorative. But this is touching the ground, the rim, and then the hammer is coming in at a given velocity. That is how we did this motion study, or this simulation. Same deal as last time, non-linear, you pick your velocities and whatnot. It should be the exact same way that you did it before. A key problem, and why I can't show these results, is they don't travel over. Do I know what's wrong? Nope. If I hit rerun, we will see that it's going to come up.
Oh, there we go. And this is just to get it going.
Okay, and there's a warning again, and more. We have 286,000 degrees of freedom. Higher that degrees of freedom, the more problems and the longer it's going to take. So I'm going to hit cancel, and that will fix your problems. So important to know, sometimes you just rerun it and cancel, you might be able to get your results back, which would help out a lot. So here we can see our von Mises. We set the hammer to be made out of tungsten. To those of you that are keen nerds amongst us, you know the hacksmith made a hammer out of tungsten, and that was part of our inspiration. Then we'll look at our displacement. Lots of displacement here. That is because this is moving. This hammer is moving, the shield is not. Then strain. It is just fine. I mean, obviously it's going to feel some, but it is a-okay. What does that tell us? That maybe the movies weren't completely crazy when they had both of these things not breaking. So we want to say a huge thank you to you all for making it to the end of the video, and we hope you learned something about how simulations work in Solidworks, some of the limitations, and how you can apply this to knowledge to your next models. Please ask us any questions. We would be more than happy to help walk you through your next simulation study. Thank you.